We're now going to add more restrictions to our counting problems, which will in turn change how we approach our solutions. First up, we're going to talk about permutations. If we have a set of n elements, a k permutation of that set is a way of choosing k elements from it. However, we're going to impose two other restrictions. One, that we cannot repeat any elements from the set, and two, that the order of the elements matter. To illustrate this idea, let's say that S consists of the 26 letters of the alphabet, and we want to look at the three permutations. So, for example, HIP, HIP, would be a valid permutation, but 2, TOO, would not because it has repeated letters. Now phi, which uses the same letters as HIP, counts as a different permutation because the order of the letters is different. So how do we count these things? We're going to use the basic counting principle, and to do this, let's set up these three different boxes, one for each different letter. If we take our bag of letters, there are 26 possible choices for our first letter. Let's say that we had chosen H. Now, having removed H from the bag, when we look at the second letter, now there are only 25 possible choices, and let's say that we take I. And finally, with both H and I gone, the last letter can only be one of 24 remaining choices. Let's say that we take P. By the basic counting principle, there are thus 26 times 25 times 24 ways of constructing a 3 permutation. And hopefully you see how this will work in general. If we're looking at the number of k permutations, we're going to multiply the first k numbers, starting with the number n. Now, mathematically, the way that we write this down is as follows. And it's a little bit abstract, but you can double check that there are in fact k numbers here that we're multiplying together. Now, a more compact way of writing this down is using factorial notation like so keep that in mind. In the above example with the 3 permutations of letters, there are 26 pick 3 possible permutations, and we can write them out as so. All right, let's ramp up the example a bit and do something a little bit more complicated. So let's suppose that you have 8 couples attending a wedding, and the front row only has 6 seats. Now, if the couples must be seated together, we want to ask ourselves, how many ways are there of arranging guests in the front row? So let's attack this by drawing out the seats. Since the couples must sit together, the first 2 seats are occupied by a single couple, and that same argument applies to the next set and the last set of seats. Now there are 8 possible couples, and we need to pick 3 of them. Order matters, and we certainly can't clone a couple to have them repeat themselves, so we're dealing with a permutation. And thus there are 8 pick 3 possible ways of choosing our 3 couples. Okay, but we're not done yet. Each couple can sit in 2 different ways. Let's say A and B are a couple. We can seat them as AB or as BA. Now this is also a permutation. It's the number of 2 permutations of a set of 2, so there are 2 pick 2 ways of seating this couple in the first 2 chairs. That same argument applies to the second and third couples as well. So if we put all of this together, the number of guest arrangements is as follows. And here we recall that 8 pick 3 is the number of ways of choosing the actual couples, and then each of these 2 pick 2s is how each couple can be seated within their designated slot, and we multiply them together to get the total number of possibilities.